Okay, so last time we were talking about this idea of path independence. Remember, the idea of path independence is that if you have one path over which you compute a vector line integral, and then another path over which you compute the same vector line integral, vector line integral of the same vector field, but over a totally different path. Right? Now, you wouldn't normally expect that these should have anything to do with each other, because look at all the different points on C1 that are distinct from all the different points on C2. Right? You wouldn't think, if you look at the individual terms that you're adding up in the summations of these integrals, they're completely different locations. And yet, merely because these two curves start at the same point and end at the same point, we get this amazing conclusion that these two line integrals are going to be equal. How could this possibly be? Highly counterintuitive, right? Now, this only works for special vector fields. This only works for gradients, right? Critically, very important. This only works for gradients. And the fact that this is a gradient allows us to draw this conclusion is that we can use the fundamental theorem of line integrals to evaluate both of these integrals, and both of these integrals are evaluated on the basis of only their starting and ending points, and the starting and ending points are the same. So that's why it works. So again, special property. This does not work for just generic vector fields, right? Only for the very special vector fields that are gradients. And just a quick reminder, this property is called path independence. Okay. All right. So now here's another true fact that is more doing to prove. So I'm just going to sort of wave at a sketch of the proof. If you want to take a look, the big idea is that you can set up an integral in a certain way. Anyway, the nice punchline is this goes both ways. So we just saw above that every gradient is path independent, and regularity issue swept under the rug. Furthermore, every path independent vector field is a gradient. So these are kind of synonymous, and again, I don't want to get bogged down in regularity issues that make a nasty, sticky wicket that's hard to deal with. But aside from discontinuities and singularities and these kinds of things, path independence and being a gradient are simultaneous. Okay, now here's another way to say it. Same statement. So yeah, you're going to notice here that I've got a starting point and an ending point that agree, and we're going to move, let's say, that direction along C1, and then this direction along C2. So these two curves start and end at the same point. Path independence is the statement that these two line integrals are equal. Now, highly modest rephrase, saying two things are equal is simultaneous with saying that their difference is zero. Right? I didn't hardly do anything there. That's a morally identical statement. But now let's look at what we have on the left-hand side here. And we've got a line integral over C1 minus the line integral over C2. Keep in mind, a minus sign is what results when you just go backwards along the curve in question. And altogether, you could rephrase this as this right here is equivalent to going along C1 and then backwards along C2. Right, so I've got this orange curve C, and the statement that this difference is zero, the statement that green minus blue is zero, is, again, exactly the same statement as this orange line integral is zero. So, different way to phrase it. This is, again, just an alternative phrasing of path independence. And for certain situations, this is really handy. That being that when for all closed curves, that closed curve line integral is zero. In other words, all circulations are zero. It's kind of an alternative way to say path independent. All right. So let me show you a situation where that's very handy. So I'm going to consider a particular vector field. We're going to think about what I'm going to call the steepness vector field. So this steepness vector field is a gradient of the altitude function, or whatever the altitude function might happen to be. Reasonable thing to call this steepness because, after all, gradients always point uphill, right? So they point in the direction of where the steepness is, and the magnitude of this vector field, magnitude of the gradient, tells you how steep it is, right? So highly plausible, I think. And I make a few observations now about this vector field. It is visibly a gradient. All gradients are path independent. And path independence, as we just saw seconds ago, means all closed line integrals are 0. Now, let's take a closer look now at this last statement, closed line integrals being 0. And in particular, let's think about what is this integrand, well, not integrand, what is this summand here, this thing that we're adding up, vector field dot displacement. Well, the vector field is the gradient of altitude function. Gradient dot displacement that's just how we compute how much that function changes. The function in question, the thing we're looking at the gradient of, altitude. So this, what I have in green, is literally just how much did your altitude change over a little piece of the curve. So grand total then, altogether, the left-hand side of this equation is just telling your total altitude change. Well, this idea then of what we're the way we've got this all set up, what we've concluded is that if you go around a closed loop, right, closed path, if you take a walk and starting it at the same point, and if you keep track of how much your altitude changes, grand total is going to be 0. And again, kind of obvious, right? Of course it is. I've never gone for a walk and come back to exactly the same point, but actually gained 100 feet of altitude. That doesn't make any sense at all. You're back to the same point. Of course you are. Right? So this concludes something that I'm going to call obvious, right? But this is the sort of mathematical immediate refutation of this idea of what I'm going to call Escher stairs. There's an artist named M.C. Escher. Many of y'all probably know his works of various sort of categories, but they're illusions and impossible drawings and things like this are strong theme. And so what we have here in this particular case, this drawing of stairs, you'll notice that the people sort of on the outside here are walking up those stairs, and then they're walking up these stairs, and then they're walking up those stairs, and they are walking up these stairs. So they have done a closed loop, and the suggestion of the drawing is that they've been gaining altitude the whole time. And that's what is impossible, right? This observation about path independence of gradients. It's just a fancy way of saying, yeah, you can't, this is nonsense. Does that make sense to everybody? Kind of cool. All right. Okay, moving along. Why do we care about path independence? It turns out that it has some really useful conceptual applications in physics and mechanics. And frankly, I think y'all know this, and I've probably said this before, but it's really valuable to know multivariable calculus before you take an E&M class. And I think that's pretty common knowledge, and I won't go off onto that. But it's also pretty handy to know before you take a mechanics class. Because in a mechanics class, they'll talk about this idea of potential energy. And it turns out that there are some deep conclusions that can be observed about the nature of energy, potential energy, and how to think about it, that come out of, fundamentally, the idea of path independence. So this is what I mean by conceptually useful. Path independence is a really valuable idea in doing certain kinds of mechanics and physics. Now, how useful is it computationally? Here and there. But here's the thing. As we just discussed, if path independence is an option, if path independence is on the table, we're talking about a gradient. that means it has an anti-gradient. And if you can just find the anti-gradient, you can use the fundamental theorem of line integrals, which is fantastic, right? Super powerful way to compute a line integral. So in some sense, now this is an overstatement for dramatic effect, but who needs path independence? It's a tool for solving a problem for which I already have an awesome tool. Right? So what's the big deal? Case could be made there. I will point out, though, that this strategy of using the fundamental theorem does require that you be able to find the anti-gradient. And I'm going to show you all how to find anti-gradients. And it works without that much trouble very often, but sometimes it can be a nasty, hairy situation. So anyway, in those circumstances, when you know that a vector field's path independent, but you can't find the anti-gradient, path independence itself can be a computational tool as follows. Here's a vector field. I'm going to take it as a given that this is path independence. I'm going to come back and talk about that in a few minutes. For the moment, let me just sweep that under the rug. I'm going to assert, we can assume that this is path independent. And we're going to look at the top half of the unit circle oriented clockwise. That's this curve right here, like that. And let's compute the resulting line integral. Okay, well now again, of course, you can brute force this. Parameterize this curve, sines and cosines. X and Y are sines and cosines, means this vector field is going to be a fair amount of sines and cosines, and of course, X prime is going to be sines and cosines. You're going to have a lot of sines and cosines, and it's going to be kind of inconvenient to compute that integral. So kind of prefer not to. Okay, here's how we're going to use path independence. Our vector field is given to be path independent. So I don't have to use that curve. I can pick a bunch of other curves. Right? Any curve that starts at the same point and ends at the same point. Take your pick. Now, I could choose that curve, and I could choose that curve. Obviously, I'm not going to. Right? But I just want to point out, you got a bazillion curves to choose from. Choose whatever's going to make your life most convenient. And I think a fairly obvious choice that's going to make our lives most convenient is to just go straight line from A to B. It's the shortest possible. It's nice and linear and such, and easy to deal with, easy to parameterize. A lot of big advantages. Okay. All right, so this is the curve C2 that I'm going to use instead. And at this point, now again, path independence being a given in this case, I don't need my given green curve anymore. Completely don't need it. I'm just going to throw it away, ignore it. I've got myself a new curve. This is pretty cool, right? Wouldn't it be nice if we could do that all the time? Again, tragically, no, can't do it all the time. This only works for specifically vector fields that we know are path independent. So anyway, okay. So at this point, it's all kind of details. There are some nice little aspects to this, to the details here. First of all, I'm going to point out that because I have picked this specific curve here, notice that y is 0 everywhere on this curve. And you can see it in how it got parameterized right there. Y is 0. So that plugs in here and makes that first component of the vector field just 0. Right? Awesome. Gotta love it. Okay. Here's the second neat thing that I think is worth noticing, and that is if you look at a dx vector on this curve, and here's some little dx vector as I move along that curve. Well, the dx vector, now of course dx is made up of components dx and dy. So rewriting dx as dx dy, but again, looking at our little dx vector here, pretty clearly horizontal. I could algebra that out by actually writing dx as x prime dt and taking the derivative of this parameterization. Not that I couldn't do that, it's easy algebra. you would find again that being as it is horizontal, you're going to get dy to equal to 0. I think it's easier just to point out, look, I can see it. It's horizontal. dy is obviously 0. Is that cool? Everybody happy with that? So that then gives us a 0 there. The dot product is then immediately 0, and we're done. Game over. Didn't have to do any, real integrating. Certainly didn't have to deal with any trig. This was a really nice solution. Is everybody happy? Okay. Now that said, let me confess. The purpose of this example was to show how path independence could be useful sometimes. That said, it remains that you can, in this case anyway, you can actually find the anti-gradient without too much trouble, right? You could probably even kind of guess it from the way it's written down. Just so what can you make up that would have this be the gradient? You'll get it if you try, right? But it's not always easy like it is in this case. Okay, moving along. What I'm going to call a local test. How do we tell if a vector field is path independent? How do we tell if a vector field is a gradient? Same thing, right? Gradient, path independent, right? Regularity issues aside, those are the same thing. So here's a wonderful theorem. The theorem says if you have a vector field that's a gradient, it follows from that the gradient that Green's operator of that vector field is 0. So call this a local test because Green's operator is something that you compute locally. Green's operator, you just compute. It's made up of derivatives. If you have a vector field, you want to compute Green's operator? Okay. Take the appropriate partials and then plug in whatever point you want locally. Doesn't matter. There's no sort of like global challenge to computing Green's operator. Whereas there is a harder test over here. I mean, finding this anti-gradient, you can't just do that one point at a time. The anti-gradient is something that has to satisfy the condition kind of one function has to work sort of everywhere, right? So that's not a local problem. Okay. So how do we know that this is true? There's a very convenient little argument I'm going to show you. We'll start by observing that these three statements here are the same. In fact, we've already observed this. Previously, we've noted that gradients are path independent and vice versa. And previously, a page back, I observed that an alternative phrasing of path independence is that all circulations are 0. All closed line intervals are 0. So those three statements are all the same. Is everybody good with that? All right. Now, recall Green's theorem. Green's theorem, here, let me undo the mess here. Green's theorem says that closed line integrals can be computed as a double integral of Green's operator. Right? So if all closed line integrals are 0, that would mean that all double integrals over two-dimensional regions are all 0. Cool? Right? Green's theorem says these two things are equal, so if that's 0, then this is 0. And now let's look at this statement over here on the right for just a second. This statement right here. All double integrals of this thing called Green's operator. All double integrals always 0? How could that be? Right? That seems kind of implied. I mean, surely there's got to be some domain where Green's operator is not 0, and then the integral is going to be not 0, right? I mean, this seems nonsensical, except in the one trivial case. There is one function that you can think of, I'll bet, for which the double integrals over every domain in the whole of R2, all the double integrals always 0. That is, in fact, the 0 function itself. It's the only continuous function that has that property. Right? Believable? Okay. All right. So thus our conclusion that you can use Green's operator, which is an easy computation, to decide on the question of whether a function is or is not a gradient, aka if the function is or is not path independent. Okay. All right. Now here's a different way of saying, kind of the short version of how to think about this argument from sort of a little bit more of an intuitive standpoint. A gradient, aka path independent, is a function where there are no circulations. Can't be any circulations. Think about this from the Escher-Stairs standpoint, for example. If it's a gradient, there can't be circulations because those circulations represent how much altitude I changed as I went on that hike. You can't change altitude grand total. What goes up must come down and all that. Right? So the left side here, I would say, could be thought of as, sort of in a, from the point of view of actually going around a curve. This is saying these vector fields don't have circulation. Now let's look at the right side over here. What does this say about my vector field? And I claim it says the same thing. It just says it from sort of an accumulation standpoint. Green's operator, of course, is circulation density. So the statement that circulation density is 0 is just a sort of an accumulation point of view on there are no circulations. So these two statements are saying the same thing, kind of in different ways. Being a gradient is saying there's no circulations in terms of keeping track of how things change as you move around the boundary. This says there are no circulations, keeping track of circulations as how they accumulate over the interior. So anyway, just a different kind of a conceptual take on what this algebra says. All right. Now, with that done, notice this is two-dimensional exclusively. Has to be two-dimensional exclusively because it's about Green's theorem. Green's theorem is, again, a peculiarity of R2. So what do we do if we're in 3 space and we want to decide if our vector field is a gradient or not? Well, we have this theorem. And again, if you want to decide if your vector field is a gradient, you resolve that question very similarly. You just compute the curl and see if you get 0. Curl instead of Green's operator. Totally analogous. And we don't quite have the tools to fill in the blanks on this yet, but in the same way that we used Green's, let's see, let me not over circle here. In the same sense that we used Green's theorem as kind of the critical link, right? The thing that sort of brings together the two sides of these collections of thoughts. Green's theorem is the linchpin of this argument in 2 dimensions. There is another theorem that we haven't covered yet that plays that role. That's the thing that holds it together in this argument down here, and it's extremely analogous to Green's theorem. It's like a 3-dimensional version of Green's theorem. And we'll get to that in Chapter 7. We're not really quite ready for that yet. Okay, so these are our tools. Make sure to know these. In R2, compute Green's operator, see if it's 0. In R3, compute the curl, see if it's 0. Example. Here's a vector field. Is it a gradient? Doesn't really leap off the page at you like the one we were looking at before, right? Other examples we've seen in the homework and such, some sort of easy ones. But in this case, how do I know if this is or isn't a gradient? And by the way, here's an approach that some people like to take to decide if there is or isn't a gradient, and that is can I find one? And that's a halfway method, right? If you can find one, then there definitely is one. If you can't find one, maybe there isn't, but maybe there is, and you're just not good at finding antigradients, right? How do you know, right? We can't just I couldn't find it, and therefore it doesn't exist. That's no fair, right? Right. So let's decide conclusively if there is an antigradient by using the theorem above. We're going to compute the curl of this vector field. Again, our vector field right here. When we compute the curl, we're going to get 3 coordinates. In some technical sense, I suppose, to be complete, we should compute all 3 coordinates. But as I started computing the curl of this vector field, this was the first coordinate of the vector field. By the way, easy partial derivatives. Right? Make sure you're good at that. Make sure you know exactly what to take the partial of with respect to what, in which order, which one do you subtract from what. Right? It's easy to lose track of that. But here you go, first coordinate of the curl, and check it out. It's already not 0. The deciding question is whether it is or is not the 0 vector. For this to be a gradient, I would need for my curl to be the 0 vector, meaning all 3 coordinates. It's not good enough for just 1 or even 2. I need all 3 coordinates to be 0. This already didn't happen. Right? First coordinate, not 0. Game over. Does that make sense? Everybody happy with that? So the curl's obviously not 0, so don't try to find an antigradient for this vector field. You're not going to find it. It isn't there. There isn't one. That's a wild goose chase. Everybody happy? Now, of course, that's a 3-dimensional example. I used curl because that's the local test in 3 dimensions. Let's think about a 2-dimensional example. Let's ask this one right here. Is this a gradient? Now, again, you might be tempted to, I'm going to try to find it. This one looks like an easy one, right? These are, I could, kind of just try to reverse engineer the partial derivatives that would make this be the gradient, and I'm going to find this thing. I can just kind of intuit it. But no, you can't. You're going to lose. You can play if you want, but you're going to lose, right? And we know that you're going to lose because look at this. I can do the local test. This is 2-dimensional, so the local test is Green's operator, which is that, which are easy partials, which gives you 2, which most importantly is not 0. So no, there is no antigradient. Don't try to find one. Even if it looks easy, don't try to find it. Yeah? All right, now just for a little bit of geometric satisfaction, now the algebra, oh, come on. Am I already? Oh, this thing's already out of juice? That's wild. Sorry, let me plug it in. Yeah, only halfway through the class. That's weird. Okay, so for a little geometric satisfaction, let's just think for a quick moment. If this were a gradient, what would that look like? Well, we have this vector field, like so. If this were a gradient, these vectors would be pointing uphill on the whatever the graph looks like of this thing. Now, can these vectors all be pointing uphill? And I say nonsense. Absolutely impossible. If that's uphill, let me start walking that way, and let me just follow the flow line around. All right, following the flow line, the vector fields are pointing along this sort of circular path. That would be your flow line. You'd be walking uphill, 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 only to come right back where you've been. Walking uphill the whole time, but you got right back to where you were. Again, that's Escher stairs. That's nonsense. That's absolutely impossible. right? So this shouldn't have an anti-gradient, right? It can't. This thing, if it had an anti-gradient, would allow for Escher stairs. Is anybody all happy with that? Does that digest well? Satisfying? By the way, you can also kind of see why Green's operator is the thing that gives it away. Green's operator being 2 that's again a measurement of how much this circulation, and ultimately again circulation here, is really the problem, right? The reason that there can't be an anti-gradient is because of a non-zero circulation. Well, Green's operator is just pointing to how that circulation, we've got a positive circulation density everywhere in the interior. Of course you're going to have a positive circulation. Like I say, different way of thinking about it. Okay. All right. I've mentioned before a really full and complete discussion of multivariable calculus in some abstract world where we had arbitrary time, which of course we don't. Really ideally should include a bunch of discussions of some sophisticated stuff that's just well beyond what we can reasonably do, certainly given the amount of time that we have, but it's also, it gets pretty sophisticated. But there's this idea of differential forms, really powerful stuff, and allows you to prove shocking, beautiful results, far-reaching, sophisticated, but ultimately very simple. Anyway, this is lovely stuff. Anyway, can't do it. So I cannot tell you all about differential forms and integrals of differential forms, etc. What I can do is take some of the ideas from that sophisticated discussion and kind of boil off all the sophistication and just kind of show you just the bones of what's really kind of, in some sense, kind of going on in that. And it leads me to this thing I like to call this strategic diagram for R2. I don't believe this is in the book, if I remember correctly. Anyway, I find this really useful. So the idea is, for sophisticated reasons that get boiled off in this process, it makes sense to compose gradient and Green's operator like this. And you may recall we talked about this, when was that? At the end of chapter 3. It's one of the last things I told y'all in chapter 3, that believe it or not, it makes sense to compose these. Put them together like this. And I talked about that this is an exact sequence. Everything has a lifetime of 2. An example of which is, if you have a vector field, and if you compute Green's operator, and you get 0, then I had something that was alive here, and now it dies here. That means it must have been born over here. Said differently, there must be a function whose gradient is that vector field. Or said differently, our vector field, because Green's operator is 0, our vector field must have an anti-gradient. Which, of course, is our local test right here that we just got through exploring. So I'm going to point out while we're here that this kind of works down here as well. What I've got down here is what I'm going to call domains over which I can compute appropriate integrals of the above objects. So, for example, I can compute an integral of a scalar valued function over a two-dimensional region. It's called a double integral, right? Like so. Likewise, I can compute an integral of a vector field over a curve. Kind of like so, for what you see right there. And the next one's not really an integral per se, but I can plug points into a function and see what comes out. And for example, I can compute f of b minus f of a, such as over there. Okay. All right. So,
Does the integrate to go left? Isn't that the partial operator?
Yeah, I haven't gotten to that yet. But the integrals kind of just go straight up and down.
Oh,
Yeah, I haven't gotten to the connection there. Yeah, the connection is to make the observation that on this level here, the boundary connects these objects, right? If you give me a two-dimensional region, the boundary of that two-dimensional region is a curve, oriented, in fact. If I have a curve now, independent of whether it's a boundary of something, just any curve at all, I can talk about the boundary points, starting and ending points on that curve. And when you kind of compose boundary like this, again, it's exact. And I have to put a little asterisk on that, but that's something y'all don't need to worry about. But exact in the sense that everything has a lifetime of 2. And I think this is actually surprisingly satisfying. Let's think about, for example, if you have a two-dimensional region. I'm going to draw an actual two-dimensional region here of sorts, if I can. Two-dimensional region, you take its boundary. Its boundary is a curve. Right? And that being said, now what happens if I take the boundary of this boundary curve and I make the observation of whether this starts and ends at the same point? So the boundary of the boundary is 0. Said differently, it kind of doesn't have a boundary. Or said differently, it's because it starts and ends at the same point, but one's the start and one's the end, it's like they cancel and disappear. So, lifetime is 2. That make sense? And it kind of, sort of tracks in some sense with the arrows are going the wrong way. Arrows are going the opposite of the direction above, but that still kind of, sort of fits. Okay. And now less obvious, let's suppose that I have some curve, whatever the curve is, some curve like that, that has boundary equal to 0, hypothetically. Right? Now, any curve, get creative, feel free, right? But any curve in two dimensions, of course, any curve whose boundary is 0, any curve that starts and ends at the same point, well, again, death, life, right? Birth, right? Because it has no boundary, because it starts and ends at the same point, it has to enclose some region. Now, it's just a geometric appeal. I'm not going to try to prove this, you know. But pretty satisfying in a way. So that's this exactness here. Okay. All right. By the way, now just for y'all's convenience, I'm going to point out this diagram. I drew it like this here in the notes, just because I wanted to have something that I could point to and kind of do some real quick stuff. But I also like having a little bit more space to work, and so here I've taken advantage of the fact that you can typeset these things and everything gets a little bit more sort of efficiently, represented, and I just get more space to do things. And so here's that same diagram pretty much. Just kind of drawn differently and expanded out in sort of the bottom section where I have these theorems. Now let me use this page to talk through these theorems, the fundamental theorem of line integrals and Green's theorem. By the way, this document that I'm going to be working on here is on the website. It's in the class materials section of the class website, not the course website, the class website. So feel free to download for your use. Here's what I'm going to call the fundamental. Oh, whoopsie! Here's the fundamental theorem of line integrals. Right, old news. I'm going to sort of sketch out what that looks like on the diagram in some sense. So, where did on this up here? Where do I start, and which arrows do I follow, and what do I plug them into, etc. And it goes like this. We start off with a function and we compute the gradient of it. Right? You can see it right there. The gradient is going to be needed there. And now, let's see, I also have to have endpoints to plug in. So let's see here. I'm going to have a curve and its resulting boundary points. Those boundary points are going to be the A and the B. And again, there you go. There's the A and there's the B. Yeah. So notice then that I am going to be taking the gradient that I computed, the curve that I started with, computing a vector line integral of that computed vector field with the given curve in vector line integral in this sense, and that gives me the right side of the equation. And then over on the other side, we'll take the function that I started with. I'll evaluate at the boundary points that I came up with, again, in this sense, and they just plug the points into the function, and that gives me that. And the fundamental theorem of line integrals says that these two things are the same. Now let me, I'm going to write all that down again, but again, just a little, sort of for convenience, a little bit faster. If you push a function forward, push a curve backward, this evaluation and this evaluation are the same. Okay, so what? Who cares? What's the point of taking our perfectly crisply stated theorem and viewing it as a sort of something that happens on a diagram? And the reason why is because it's the exact same diagram if you do Green's theorem instead. So Green's theorem says that I have a vector field for which I compute Green's operator. You can see it right there. I have a two-dimensional region for which I compute the boundary curve. Again, right there. And again, evaluate on both sides. So both of these theorems, let's see here. Both of these theorems look like push forward for the integrand, push back for the domains using boundary, and then sorry, I wanted a different color. The left evaluation equals the right evaluation. And this is what people started to notice not long after Green's theorem and the fundamental theorem of line integrals came out. That's like, well, yeah, they're different. One's about double integrals, one's about vector line integrals and boundary points, and geometrically, yeah, they're totally different contexts. But oh my gosh, look at the analogy. This couldn't possibly be a coincidence. How could these two theorems look so much alike when you put them? When you kind of just arrange things in this fairly natural way, right? And all of a sudden these two theorems are identical. That's not a coincidence, right? And again, the question loomed for a very long time as to how could this be? What's the connection between these theorems? And it was I think it was in the 1930s or 40s, somewhere along in there. Not that long ago, right? My dad was alive, right, when the mathematical community finally figured out why this connection, why this analogy works. So it's recent, sophisticated ideas. And again, that's why I can't show it to you in this context. All right. Okay. I also really like, by the way, and this is just a personal preference, but I like to be able to use a diagram to kind of organize ideas. So I'm going to show you an example of this. I'm going to talk about these special vector fields, and again, you can describe these special vector fields in different ways. So let's talk through these special vector fields. We've talked about how gradients, right, are also Irrotational. Keep in mind what irrotational means. Where am I? Here we go. Irrotational. This is just a quick reminder, but irrotational means this. Green's operator, after all, is a way of measuring, in some sense, how much of a rotational aspect there is in the fluid that's flowing according to the vector field. And if the amount of a sort of a rotational story that's happening in the vector field is zero, if there is no rotational aspect to the fluid, then irrotational is a pretty reasonable choice of words. And just to sort of be explicit about that, I like to color code like this. Right? Irrotational. It just fits. Right? Very natural choice of words. Okay, Green's operator is equal to 0. And then we've also observed that these are path-independent vector fields. Now you can say these words and you can kind of write them down like this, and that's fine, but everybody's different in how they understand things and digest things and remember things. I personally find this easier to remember in terms of how these ideas fit on the diagram. Our special vector fields that live here, things that you would naturally want to compute vector line integrals of, in other words. Our special vector fields are the ones that are the gradient of something, which, by the way, identically means they're vector fields for which Green's operator is 0, which, by the way, means that they're path independent, and path independent I have to kind of hack to make show up on the diagram. Path independence says that if you have two curves that have identical boundaries, then you get the same value for the vector line integral. So that's just, I don't know, that's how I like to draw it on the diagram. So these three ideas that you can see on the diagram are just saying what I have in purple here. Special vector fields have all three of these properties. And here they are, and here are their three properties. That's kind of a way of keeping track. If you're not persuaded, or if your head doesn't just work that way, and that's totally fine. I mean, I myself understand. I like diagrams to visualize what's where and what's going on. But everybody's different, and that's no problem. Let's see here. Let me do this. I'm going to draw your attention down here real quick. We are going to have a three-dimensional version of the diagram that I was just showing you. It's going to take us some time, but we've got to develop, first of all, what is this critter? We haven't even seen that before, right? So we've got a ways to go before we can make sense out of this diagram. But just to hopefully be persuasive that this is a useful idea, I'm going to point out the following, and that is this pattern of special vector fields in 2 dimensions. It's going to turn out that the exact same pattern holds in 3 dimensions, and even more shocking, the exact same pattern happens when you move over, when you increase the dimension and are talking about 3-dimensional solids with 2-dimensional boundary surfaces, and then related to that, surfaces that have boundary curves. This pattern holds perfectly. And that's, again, a real eyebrow raiser, right? That how could this possibly be? Okay, and I think there's a lot of good ideas to be had there. Okay. All right. Now let's see here. I do not have. I was going to say I have 5 minutes, but I don't. Let's see here. I have 48 seconds. Okay. We've already kind of talked through most of those ideas. You know what? This is a pretty good place to draw the line. I'm sure I owe y'all time anyway. We'll draw the line right here. Pick up here on Wednesday. Y'all have a good one. See you later.